Hey everybody, I'm going to give you a little bit of an intro into solving problems related to transistors. And we'll have a look at an example and some of the terminology around transistors. So hope you enjoy this video. What we have is a symbol of a couple transistors. Now these transistors are very similar, except that this arrow in the symbol determines which part of the transistor is a negative type material. And so the tip of this arrow points to the negative type material. And in this case, we have an NPN type transistor. So an N because the arrow is pointing down here, and then P in the middle, then N up here at the collector. This symbol has the tip of the arrow pointing inwards towards the N type material. So this transistor would be a PNP type transistor. So the arrow always points towards the N type material. Mathematically, this doesn't make a difference, but the important thing is that in order for the transistors to be triggered, we have to make sure that the power supply, the negative and the positive, are orientated correctly with respect to the negative material. So current has to flow into the tip of that arrow. So for example, the negative of the power supply would be here, the positive would be here, current would be flowing into the tip if we're using electron flow. And over here, the negative would be up here in the collector, and current would be flowing down into the tip of that arrow. And that's to trigger conduction. Here I have another example, or a example of the transistor put into a circuit. Now this will be an NPN type transistor, and I could have used a PNP, doesn't really matter. As I mentioned before, it's really important that our orientation of the power supply be correct, or we're not going to get conduction. So the negative has to flow into the tip of that arrow, or be orientated to the tip of the arrow. A silicon transistor would have a voltage drop of 0.7 volts across this junction here. And we call this junction the emitter to base junction. If you remember up here on the symbols, we had the emitter, the collector, and the base. So ECB, and the same here, even though this is a PNP type, emitter, collector, and base. If I have a power supply of 10 volts and I'm going around the outer loop here, I would know that 10 minus 9.3 would give me, or 10 minus 0.7 would give me 9.3 volts at the base. Take a look at this circuit for a minute. You'll see that there's two paths. There's an outer path, so it goes from the emitter into the emitter, out of the base, around and back to the positive, or the inner loop leaves the negative, goes in through the emitter, up through the collector, through the load, and then back to the positive. So it's kind of like two parallel paths. What we have to remember is that with a transistor, if there's no current flowing through the emitter to base, it doesn't actually turn on or close the junction between emitter and collector. So we absolutely have to have current flow through the outer circuit to get current flow through the inner circuit. So current flow through the emitter to base triggers conduction flow from the emitter to collector. Now, beta is the relationship between the current flow in the base and the current flow through the collector. There's a multiplication factor, and they give that to us in the data, which is beta. Often beta is not mentioned, in which case we assume that it's 100. That means that whatever current is flowing here through the base resistor, 100 times that would flow through the collector. So if we have 0 flowing through the base, we're going to have 0 flowing up through the collector. If we have 1 amp flowing through the base, we'll have 100 times that, or 100 amps flowing through the collector. Typically, we don't get into those kind of amperages. All right, so we know that 0.7 volts is dropped from emitter to base. That's typical for a silicone transistor. And we know that beta is a relationship between the current through the collector and the current through the base. This is the formula that we can use. Beta equals IC over IB. I like to remember the B is on the bottom. IC is the current through the collector. IB is the current through the base. Let's take it a little bit further. All right, so we had the same circuit on the, I put some values in here. So we had 10 volts. I'm pretending that my load is 15 ohms and my resistor of the base is 6,000. So how did I calculate all of this out? Well, if I took 10 volts and I wanted to find the voltage of the base, what I can do is I know that 0.7 volts, so we assume this and we just plunk it in there. 0.7 volts is the emitter to base voltage. 10 minus 0.7 gives me the 9.3, and that's going to be my voltage at the base. So then I already had 6,000, that was a given to me. So now 9.3 divided by 0.0015, sorry, 9.3 volts divided by 6,000 gives me a current of 0.00155 amps. Now I know the current through the base. We're assuming that beta is 100, and that means that the current through the collector will be 100 times larger than this. So I can just take this and multiply it by 100. And that would give me my 0.155. Now we can also use the formula, beta equals IC over IB. We're assuming 100 for beta. IC is what we're looking for, and we had already found IB. So then 100 times 0.00155 amps would give me IC, which is 0.155 amps. Now, if you notice that the current flow coming on this inner loop up through the emitter, out of the collector, it also flows through what I'm calling my load. And so IC is also the current of the load. So I load. The next step is to find the voltage at the load. I was given 15 ohms. I just calculated 0.155 amps. Using Ohm's law, E of the load will be I of the load times R of the load. And so 0.155 times 15 ohms will give me 2.33 volts. Now this is an inner loop. And so Kirchhoff's voltage law says that that inner loop also has to equal 0. So we start with a power supply of 10 volts plus a drop of something here, and a drop of something here has to equal 0. We just calculated 0.33 volts. And so to figure out this 7.68 volts, it's 10 volts minus what we just calculated for I of the load, 2.33 volts, gives me the voltage 7.68. That is a voltage drop across this junction here, the emitter to collector junction. So all of this meets Kirchhoff's voltage law, which says around any closed loop, the algebraic sum of the voltages equals 0. And if we look down here, we had 10 volts as a supply, plus 0.7 volts as our drop across the emitter to base junction, and another 9.3 volts at our base, that equals 0. Or the inner loop, 10 volts was our supply, plus a drop across the emitter to collector junction and the drop across our load, and that equals 0 as well. So just looking up here, outer loop, 10 minus 0.7 minus 9.3 gives us 0, or the inner loop 10 minus 7.8, sorry, 7.68 minus 2.33 also gives us 0. I hope that's helpful.